Okay, so we're getting into using similarity with right triangles. So this is our first set of notes in Unit 9. We're going to start by defining something that's called a geometric mean. Let's say I have three numbers, a, b, and x, and they set up so that a is to x as x is to b. Then we say that x is the geometric mean of a and b. Or another way of saying this is that if x is equal to the positive square root of a times b, then x is the geometric mean. This is what you would get by cross multiplying and then taking a square root. Okay, so we're going to relate this to a bit of a theorem about right triangles. Okay, so in our theorem here, we're going to say if I have a right triangle. Okay, so there's my right triangle with the right angle up here. And I drop an altitude, right? And this is A, N, B, C. Then these triangles, triangle ACB, that's an altitude, and triangle ANC and triangle NCB, I think. Oh, I wrote it as, CNB. There we go. Let's make it that way. Are all similar. Okay, so let's look at what's going on here. So let's take, basically we're saying that this small triangle here, this small triangle here, and the large triangle all have to be similar. So if I take the small one to the really big one, they both have angle A, and they both have a right angle. So that gets me two angles. That makes them similar by AA similarity. If I take the medium size one to the great big one, they both have angle B, and they both have a right angle, which makes them similar. So if the small one's similar to the big one, and the medium sized one is also similar to the big one, all three of them must be similar to each other. Alright, so we get a couple of corollaries from this, and they're pretty useful and straightforward. Okay, so the first one says that, that's the first corollary. Alright, the first one says that if I drop an altitude to a right triangle, okay, then the length of the altitude is the geometric mean between the segments of the hypotenuse. So if I call this x, and I call this m, and I call this n, then x has to be the geometric mean of m and n. And that directly follows from the similarity, because if the small triangle and the medium-sized triangle are similar, then m is to x as x is to n, and that results into that geometric mean. The second corollary, given the same drawing, okay, so we're going to call this C down here. Okay, actually, we don't need that for this, so we're going to get rid of it. We're going to call this one A. We're going to call this one B. Says that the leg, each leg is the geometric mean between the hypotenuse, so I do need the length C, the hypotenuse, and the part of the hypotenuse adjacent to that leg. So A is the geometric mean of M and C, and B is the geometric mean of N and C. Okay, another way of looking at this is, remember that A is to M, right? Sorry, m is to a, right? Short is to hypotenuse, as a is to c, and that's going to give me the first one. And in the second one, b is to n, as c is to b, so that's going to give me the second one here. Now, just a little interesting note. If you play out these statements kind of together, these two, something interesting happens. If I take a squared, right, and I say plus b squared, that should be mc squared, right, plus nc squared, I think, yeah, or square root of mc squared, square root of nc squared, right? So if I square something that has been square rooted, I get mc plus nc. And if you look at that, the c comes out, giving me m plus n. But lo and behold, m plus n is the same as c, so that's c times c, which is ultimately c squared. So this actually proves a squared plus b squared equals c squared. This is another proof of the Pythagorean theorem. So there's a little bonus in there. This is, in fact, how Pythagoras himself did prove it, based on Euclid's elements, not the way that we proved it earlier in class. So there's a little historical note, something that maybe you can see from what we're doing here. All right, so that's it. That's the end of that section.